Hello, welcome back to the second course in physics. And this is going to be the second lecture on RC, RL, and RLC circuits, first order alternating current circuits, and second order alternating current circuits. And here we will be finishing the discussion of first order circuits, and then we will move to second order circuits. And the contents of this lecture will include AC first order circuits. First of all, as we mentioned, we will consider a more general discussion of the RC circuits with alternating currents and RL circuits with alternating currents. And then we will discuss the AC second order circuits. We will evaluate the homogeneous solution, and then the particular solution or the steady state solution will be evaluated. And finally, we will talk about resonance and the resonance phenomenon in AC circuits. Now let's go back to the AC first order circuits and the solutions that we have developed in the last lecture. In the previous lecture, we will start from that solution and start building on it and discussing the different cases of circuits and initial conditions. So in the case of an alternating sinusoidal electromotive force, previously in the last lecture we considered that the power supply has a constant electromotive force. But in the case of an alternating sinusoidal electromotive force, we remember that the homogeneous solution stays the same, which is the transient solution, because the transient solution is the solution of the homogeneous differential equation where the source is removed from the equation. And now only the particular part which involves the source is the one that will involve some more calculation. Integration and integral methodology is needed to do the solution. And in this case of sinusoidal motion, source, we assume that chi of t, that function that we talked about, is of the form of chi naught times cosine omega t. It's some sort of a sinusoidal supply of power. And we assume that the steady state solution takes this form of the cosinusoidal form because this is essentially will be the prominent shape of the solution. It's the steady state solution. So we assume that psi, the steady state or the particular solution, is of the form psi naught times cosine omega t minus phi, where psi naught and phi are constants. And now if we evaluate phi and psi naught, then the solution is fully determined. So we start from here, from this assumption, and then we put this solution into the differential equation. We get minus t times psi naught omega sine omega t minus phi plus psi naught cosine omega t minus phi. That is equal to u of t, which is chi naught times cosine omega t. So this is the differential equation with this assumed solution in it. And now we are after determining this solution, basically determining psi naught and phi. That's what we are after. Now, we expand the trigonometric functions. This sine omega t minus phi, for example, is equal to sine omega t cosine phi minus cosine omega t sine phi. Similarly, cosine omega t minus phi is equal to cosine omega t cosine phi plus sine omega t sine phi. So we have functions in both sides of the equation, functions of some terms containing sine omega t, some other terms containing cosine omega t. So we expand the trigonometric expressions containing sine and cosine omega t minus phi, and we equate the coefficients of the sine omega t by itself, because this will be true for any time at any time t. So the coefficients of the sine omega t in both sides of the equation will be equal. And similarly, the coefficients of the cosine omega t on both sides of the equation will be equal. So we equate these coefficients in both sides of the equation, and we obtain two equations, one from the coefficients of sine omega t, one from the coefficients of cosine omega t. And these two equations are solved. They contain psi naught and phi. They are solved simultaneously, and we obtain psi naught and phi, which is the desirable solution. By determining phi and psi, we get the solution fully. That's what we do. So first of all, after we expand the trigonometric functions, we equate the coefficients of sine omega t from both sides of the equation. And that gives us psi naught sine phi minus tau psi naught omega cosine phi is equal to 0, because we don't have any term containing sine omega t in the right-hand side of the equation. The right-hand side of the equation only contains cosine omega t. So from this equation, we can get the value of phi, which is one of the unknown values. Tan phi, tangent phi, is equal to omega t. This is a solution of this equation. So this is the first undetermined unknown, phi. It is known now. It is solved because t is known. Tau is known. It's simply the time constant of the circuit. If it's an RC circuit, it's RC. If it's an RL circuit, it's L over R. So from this, of course, tangent phi is equal to omega t. And from the relations, sine phi is equal to tangent phi over the square root of 1 plus tangent square phi. We can determine sine phi is equal to omega tau divided by 1 plus omega tau squared, all under the square root. And cosine phi is equal to 1 over 1 plus tangent squared phi under root. And this gives cosine phi is equal to 1 over square root of 1 plus omega t squared. So with these in mind, these are required in order to solve for psi naught. Now from the coefficients, this is the second equation, from the coefficients of cosine omega t, we obtain psi naught cosine phi plus tau psi naught omega sine phi is equal to chi naught. This is from the coefficients of cosine omega t. And this gives us psi naught in terms of chi naught and omega and sine phi and cosine phi. But we replace sine phi and cosine phi by their values in terms of omega t, and we get this result: psi naught is equal to chi naught over the square root of 1 plus omega t squared, omega tau squared. So this is psi naught. Now we have determined psi naught, we have determined phi. That means the solution is fully determined. That's the solution. And now we apply this solution to the special case, because this is a general solution regardless of what type of circuit we have. We are solving the general equation. Now apply this solution to the RC circuit, for example. And in the case of the RC circuit, what do we have? We consider the parameters. We consider U, the power, the voltage is given by V naught cosine omega t. Thus, chi of t is equal to V naught cosine omega t, which means that chi naught is equal to V naught. And in this case, in the RC case, the time constant tau is equal to RC. So with these values put together, the solution, the steady state solution for the RC circuit is psi, which is equal to Q over C, as we mentioned in the previous lecture. That is equal to substituting for chi naught and tau, we get V naught over omega C times the square root of R squared plus 1 over omega C squared. Here we used to have omega C times R all squared. So we take omega C outside, and we are left with this value, times cosine omega t minus phi. And now if we look at this quantity under the square root, this is the square root of resistance square plus the reactance x sub c square. So it's like the vector addition. It's like a vector addition of two resistances in perpendicular to each other. So this is like a resistance, which is the addition of these two resistances in vector form, and these two resistances are perpendicular to each other. And thus, if we rewrite this quantity under the square root as z, then we get Q is equal to V naught over omega over z. Z is this quantity under the square root times cosine omega t minus phi. And here, z, this quantity, which is square root of r squared plus 1 over omega c square, is the impedance of the circuit. And this impedance is resembling, as we mentioned, the addition of two perpendicular resistance components, as if we have two resistors. One of them is the resistance of the resistor R, and one of them is the resistance of the capacitor C, which is 1 over C, and in perpendicular, making 90 degrees. It's something like that. And now the current in the circuit is obtained by deriving Q, dQ by dt is equal to minus V naught over Z times sine omega t minus phi. And the minus sine omega t minus phi can be rewritten as cosine omega t minus phi plus 90 degrees. So we notice that the phase difference between the voltage, the applied voltage, which is cosine omega t, and between the phase of the current, which is omega t minus phi plus 90, we notice that the current is ahead of the voltage. It leads the voltage by the angle, by the phase gamma, or the angle gamma equals 90 minus phi, which is smaller than 90 degrees. So in this case, the current in the capacitor, in the circuit, it leads the voltage across the capacitor by this phase difference, which is less than a quarter of a circle. And tangent gamma, this phase difference, is equal to cotangent phi. By this, from knowledge of this value, it's 90 minus phi, which is equal to the reactance of the capacitor x sub c over r. This is the value of gamma. So we can, from here, we can determine this phase difference from knowledge of the reactance of the capacitance and the resistor in the circuit. And now we can apply these principles to the RL circuit. And in this case, in the RL circuit case, we have an electromotive force that is alternating also. And in this case, chi of t is equal to u over r, as we have mentioned previously in the previous lecture, which is equal to v naught over r times cosine omega t. This is the time-dependent function in the right-hand side of the differential equation, of the general differential equation. And here we obtain the same general solution, but we can replace it in the case of RL. We can replace for the tau, the time constant. Tau is equal to L over R, and chi naught in the case of RL is simply V naught over R. So if we substitute these in the general solution is known, we can get the right solution for the RL circuits. And so the solution for the case of the RL circuit is simply psi s in the steady state solution, and psi in the case of the RL is simply the current I, as we have mentioned before. So this is equal to substituting for the values of chi naught and so on, and tau, we get V naught over the square root of r squared plus omega L square times cosine omega t minus phi. That's the current that is flowing in the RL circuit. And again, we notice that this current is equal to V naught divided by this square root of r squared plus omega L square. So that means this square root has the dimension of a resistance R, and it's like r squared plus x sub L, the reactance of the inductor, square. So it looks like a resistance that is resulting from the addition of two resistors that are perpendicular to each other. One of them is the resistance of the resistor R, and the other one is the reactance of the inductor, omega L, and they are perpendicular. And so it's like V over a resistance. And this resistance, again, is the impedance Z of the circuit, of the RL circuit, where the impedance is equal, Z is equal to the square root of R squared plus omega L square, or XL square, the reactance of the inductor L. And in this case, we notice by looking at the phase of the current and comparing it with the phase of the applied voltage, which is omega t, we have seen that the current lags behind. It lags behind the voltage by an angle phi, which is less than 90 degrees. And the current is written as V naught over Z, which is the impedance of the circuit, times cosine omega t minus phi. And tangent phi is simply XL over R. This is in the case of RL circuit. And now we have finished the discussion of the first order circuits, and we move now to second order circuits. Second order circuits which include both inductors and capacitors, and maybe resistors too, resistance R. So these circuits are they are represented by second order differential equations. And in this case, for an RLC circuit or LRC circuit, we have a voltage that is dependent on time, and we have a resistance and an inductor and a capacitor. And in this case, the differential equation that represents this circuit is the potential obtained from the power supply, the applied potential or the electromotive force that is oscillating in time is V naught cosine omega t. That's equal to the potential drop in the inductor, which is L di by dt, plus the potential drop in the resistor, which is Ri, plus the potential in across the capacitor, which is Q over C. And notice that here I and Q are correlated by a first derivative, where I is equal to dq by dt. So we have now both I and Q. We cannot do that. So we can differentiate all over with respect to t in order to homogenize these variables to obtain only one variable. So if we differentiate, this will be second differential of the current. This is the first derivative of the current, and this will be dq by dt is the current, simply the current. So making this derivative again, it becomes L d2I by dt square plus R di by dt plus 1 over C times I, which is coming from dq by dt, is equal to minus V naught omega sine omega t. That's coming from differentiation of the right-hand side of the equation. So this is a second order inhomogeneous differential equation. And we solve it by solving both parts. First of all, we solve the homogeneous part, and then we solve the particular solution or the steady state solution. As for the homogeneous part is a solution of this homogeneous equation. LC, we just rearrange it. LC di d2i by dt squared plus rc di by dt plus I is equal to 0. And this can be rewritten as a constant a, which is LC in this case, a times the differential square. If we substitute d by dt as a differential operator, we write, instead of d by dt, the differential operator, we write capital D. This is a differential operator. It means d by dt. So this is d square. It's this differential operator square or applied twice to the current I, plus b, which is in this case RC, times the differential operator d applied to I, plus 1. Here I is simply, there is an operator 1 multiplied by the current I. This is equal to 0. And notice that an a and b both are positive constants. LC and RC, they are positive constants. Now we are interested in solving this second order differential equation. And the solution, since it is a second order differential equation, it has a d square in it. So in general, we have two roots. We have two solutions, two roots for this equation. And how do we solve this equation? We assume a solution of the form I is of the form of e exponential to the RT. If we assume this solution, we put it back into the differential equation, we get a times r squared, r is the root here, plus b times r plus 1 is equal to 0. So this satisfies the solution. So this can be solved algebraically. This equation can be solved algebraically, and we can find the values of r, which are the roots of the solution, that satisfy the solution, that satisfies the homogeneous differential equation, that is. And the solution of this equation is, finding the roots, is simply r is equal to minus b plus or minus square root b squared minus 4a divided by 2a, the well-known solution, where b squared minus 4a is the delta, is the discriminator, called the discriminator delta. And here r1, we have two roots, as we notice. r1 is equal to minus b plus root b squared minus 4a over 2a. This is the root 1. And the second solution, or the second root, is r2 is equal to minus b minus square root of b squared minus 4a over 2a. And we have here different cases depending on this discriminator, which is square root of b squared minus 4a. What is the value? Because b and a are variable in general. One of them can be larger than the other or whatever. So we have different cases. For example, the first case, if b and a are related in such a way that delta, which is b squared minus 4a, is equal to 0. In this case, if this discriminator is equal to 0, in this case, r1 and r2 are equal. And both of them, each one of them is equal to minus b over 2a. And in this case, the solution of the differential equation, is the homogeneous solution, is I sub h for the homogeneous solution. It simply equals to a constant plus a second constant times the time t, all multiplied by the exponential of rt, where we have the roots are, the two roots are the same, r. It's simply r. So this is the solution in this case where the discriminator is equal to 0, and this case is called a critically damped case, a critically damped solution, critical damping situation. And in case 2, we have, in the case delta does not equal to 0, then r1 and r2 are not equal in general, and we have the homogeneous solution is given by IH is equal to a e to the e to the power r1t plus another constant b times the exponential of r2, which is the root, the second root, times the time t. So this is the general solution in the case when the discriminator is not equal to 0. And here we have two cases when the discriminator is not 0. Either the discriminator is positive or the discriminator is negative. If the discriminator is positive, then we have the so-called overdamped case or overdamped solution. If b squared minus 4a is greater than 0, then we have the overdamped case where R1 and R2 are both negative solutions. The solution is exponentially decaying, where omega 1, we can rewrite the roots of the solution in another form. Omega 1, write it as b minus square root of delta, where delta is positive here, over 2a, and omega 2 is equal to b plus square root of delta over 2a. And then the solution, the homogeneous solution, is given by, in this case, I homogeneous is equal to a times e to the minus omega 1t plus b e to the minus omega 2t. Here we replace the roots by omega 1 and omega 2, where omega 1 and omega 2 are both positive quantities. And then the homogeneous solution is exponentially decaying with time. So this is the overdamped solution when the discriminator is greater than 0. And now we have the other case where the discriminator is negative. If the discriminator is negative, then we have the underdamped solution. And in this case, when the discriminator is negative, the square root of a negative quantity is imaginary. So we can assume that this quantity, b squared minus 4a, is, we can assume, because it's negative, we can assume that it's equal to minus 1 times 4a minus b squared. And minus 1, when we take the square root of minus 1, it gives you the imaginary component j, we call it, the imaginary number, which is square root of minus 1. And 4a minus b squared is positive. And now we can rewrite the roots in this form. R1 is equal to minus b plus j, which is the square root of minus 1, times the square root of 4a minus b squared, which is positive now. This quantity is positive, but this is the complex number, a complex number because of this j, which is the square root of minus 1, over 2a. And R2 is equal to minus b minus j times the square root of 4a minus b squared over 2a. These are the two roots which give the solution. And now this solution gives a damped oscillatory solution, because the term minus b over 2a, in this case, it gives a damping solution, which is going down with time. And this complex number, exponential to a complex number, is an oscillatory solution. So we have the solution is a combined damping and oscillation and oscillating solution. So that's why it's called a damped oscillatory solution. And the solution can be rewritten by decoupling removing the damping side from the oscillatory side or the oscillatory part, and can be rewritten as e to the minus omega naught t, where omega naught is the b over 2a, which exists in both roots, times, in parentheses, because we have a constant, times e to the power j times some root plus some another constant times e to the minus j times the same root. This can be rewritten in the form of a cosine and a sine function as a cosine omega c t plus b sine omega c t, an oscillatory solution. And here in this solution we have used the symbols omega naught to indicate b over 2a, and omega c here is simply the square root of 4a minus b squared over 2a. That gives the full solution in this case, the underdamped case. And if we plot I homogeneous with time, the behavior of the current goes like this. It's oscillatory, but the amplitude of the current is decreasing in time, oscillatory and decreasing. And the period of oscillation, which is the time between two minima or the time between two maxima, this period, t sub c, is equal to 2 pi over omega c. It's defined by this, the frequency in the oscillatory part. So this is for the homogeneous solution. And now, as far as the particular solution is concerned, of course, we have L d2i by dt squared plus R di by dt plus 1 over Ci is equal to minus V naught omega sine omega t. Now we take this contribution of the inhomogeneous part, we take it into consideration, and we have solved for the transient solution, which is a damping solution, regardless whether it's oscillatory damping or critically damping or over damping. It's a damping solution that goes to zero as time goes. We are left with this oscillatory term as time goes. And the particular solution, we assume that it is sinusoidal because it's taking the same form as the potential here, as the voltage, because this is the remaining as time goes. So it is going to be oscillatory in time. And we assume that the particular solution, or the steady state solution, IP is equal to I naught cosine omega t minus phi. And now solution, if we determine I naught and phi, then the solution is fully determined. So this is what we are after, just determining what's I naught and what's phi, and that gives us the full solution of the current of the circuit, the particular solution of the current of the circuit. And now we put that solution, that assumed solution, into the differential equation. We rearrange these terms, and we get 1 minus omega squared LC all times I naught cosine omega t minus phi minus omega r c I naught sine omega t minus phi. That is equal to minus omega c times v naught times sine omega t. And what we do here is exactly what we have done in the first order case. We expand the trigonometric functions, the cosine omega t minus phi and the sine omega t minus phi, into its components, and we equate the coefficients of the sine omega t in both sides of the equation and the cosine omega t in both sides of the equation. We equate the coefficients and we determine the unknowns, and thus we obtain the desired solution. That's what we do. So we equate the coefficients of cosine omega t, and equating these coefficients will give us, just we write instead of omega L, for example, we write XL, and instead of 1 over omega c, we write X sub c, the reactance, instead of writing it in component form. So this gives minus XL minus XC times cosine phi plus R times sine phi is equal to 0. And this gives us a solution for phi. Tangent phi is equal to XL minus XC over R. That is equal to X over R, where X is equal XL minus XC. XL is the reactance of the inductor, XC is the reactance of the capacitor. So X, which is the summation of these reactances, taking into consideration the directions of them, is simply the reactance, the total reactance of the circuit. So the reactance of the circuit divided by R gives tangent phi, this undetermined coefficient. And now equating the coefficients of sine omega t, we get xl minus xc I naught sine phi plus r I naught cosine phi is equal to v naught. And having in mind what is sine phi and cosine phi in terms of tangent phi, this gives us I naught is equal to v naught over z, which is v naught over square root of r square plus the reactance x square, which is xl minus x sub c square. So v over z, v naught over z simply is I naught. So thus we determine I naught, we determine phi, and thus the solution is fully determined. The particular solution is fully determined. And now we move to talk about the last topic in this lecture, which is resonance. Now we just have to remember that the reactance of the circuit is frequency dependent, because x is equal to xl minus xc, which is omega l minus 1 over omega c. It is frequency dependent. So the impedance, which is the square root of r square plus x square, this x square, the impedance will be minimum if the reactance of the circuit, if x is equal to 0. If the reactance is 0, then the impedance in the circuit is minimum. And if the impedance is minimum, then the current is maximum. We obtain a maximum current in the circuit. And under this condition, when x, the reactance, is 0, the reactance is 0 at a given frequency, we call it omega naught, and that is the resonance frequency. And we say that under this condition, when the reactance is 0, we say that the circuit is resonating. It's in a resonance condition. And the frequency omega naught is the frequency of resonance. And the frequency of resonance can be obtained by setting x equals to 0, which means omega naught L minus 1 over omega naught C is equal to 0. That means omega naught is equal to 1 over square root of R of LC. That is the resonance frequency of the circuit. So setting this, the frequency of the circuit or the power supply, setting the frequency of the power supply at this frequency, we will get the maximum current delivered into the circuit. Notice that in resonance, the impedance at resonance, z as a function of omega, z is a function of frequency, of course. If we set the frequency equals omega naught, then x is equal to 0, and thus z, the impedance of the circuit, is equal to simply r, the linear resistance. And notice that also phi, from the formula for phi, tangent phi is equal to x over r. If the x is equal to 0, then phi is equal to 0. Tangent phi is equal to 0, then phi at resonance is equal to 0. That means the current and the voltage are in phase. And now if we are off resonance, then if omega is larger than omega naught, we say that the circuit is inductive, because in this case the reactance of the inductor is higher than the reactance of the capacitor, and the behavior, it looks like inductive rather than capacitive. That is, if omega is larger than omega naught, than the resonance frequency, and vice versa, if omega is smaller than the resonance frequency, then the circuit is called capacitive, because in this case, the reactance of the capacitance is larger than the reactance of the inductor, and the behavior of the circuit is like a capacitive circuit rather than an inductive circuit. And now we define the dimensionless quantity that is called the quality factor of the circuit. And this quality factor is simply defined as Q naught equals 1 over R times the square root of L over C. Notice that if we multiply L by omega and C by omega, so we are doing nothing here. L omega is simply reactance, the reactance of the inductor, which has dimensions of resistance, and 1 over omega C is also the reactance of the capacitor, which has also a dimension of R, of resistance. So this L over C has dimensions of R square divided by R, so it has no dimensions. This is the quality factor of the circuit. And what is the significance of this quality factor? The normalized current I naught over V naught over R. V naught over R is the maximum current that we can get, which is the current at resonance, as we have mentioned a little bit earlier. The normalized current, the current in the circuit at any frequency, normalized to the maximum at resonance, that is, the normalized current amplitude is sharper. The signal is sharper for a higher quality factor. So if we look for the solution for the current, and we set, for example, Q naught, the quality factor, we set it equal to 1, then we get this behavior for the current, normalized to the maximum current. And if we set Q naught equals to 5, we get a sharper signal for the current. And indeed, this gives us an idea that if we have a circuit with a very large quality factor, that means a very small resistance with respect to root L over C, that means very large L over C ratio with respect to the resistance R. If we have such a circuit, then that circuit will provide us with a very, very sharp signal for the current around the resonance, and that is the principle of the tuning of the circuits of our appliances, like, for example, the radio or the TV. So the tuning for a radio, for example, for a radio receiver, is an application for this principle. And in this case, in the case of tuning radios, a Q naught is larger than 100 for this circuit. At this point, I would like to end my lecture and thank you for your attention.